All right, so second induction proof of an inequality doesn't look dissimilar to the one I did in the previous video. It's n squared rather than 4 to the power of n. So the kind of this bit here, this kind of trick almost to solve it, this logical step in solving it is going to be the same for this one. The 3 steps are going to be the same as ever. And then just at the end of this one, I'm going to talk about the difference between the k and the n here. Just people might be a little bit unsure about that or a little bit confused about that you're going to go from the 12th to the greater than 2. But anyway, from the start here, as I said, on these inequality ones a lot, it's not 1 you're subbing in for the first step. In this case, it's 5. They will always tell you for these ones, okay? There was 1, I think, in the divisibility ones where it was 0, and you had to kind of, or the series ones, I think, where it was 0, and you had to figure that out yourself just because of what the first term was. But this one here is telling you 5 is the first number this works for. So, first step is to show P5 is true. So 5 squared is greater than 4 times 5 plus 3. 5 squared is 25. 4 times 5 is 20. Sorry, that should be 4 times 5 plus 3. 4 times 5 is 20 plus 3 is 23. 25 is greater than 23, so P5 is true. Next is to assume PK is true. So that is k squared is greater than 4k plus 3. Third step, prove pk plus 1. So instead of k squared, I've got k plus 1 squared. Instead of 4 times k, I've got 4 times k plus 1 plus 3 then. K plus 1 squared, so k squared plus 2k plus 1 is greater than 4 times k is 4k, 4 times 1 is 4, plus 3 at the end. So again, I'm not going to be kind of subbing in for k squared just because this is an inequality rather than an equation. But I am going to try and get k squared greater than here and k squared greater than here and then link them. Okay, so I want to just get k squared on the left hand side to make this look a bit like this. So leave k squared where it is greater than, so I've got 4k on the right hand side, I bring 2k over, it becomes minus 2k, so 4k minus 2k is 2k, 4 plus 3 is 7, bring the plus 1 over, 7 minus 1 is 6, and that's what I'm trying to prove. So I'm going to bring this down and just compare them. So from pk, k squared is greater than 4k plus 3, and that's my assumed to be true. You mightn't see this kind of explicitly written in other solutions, but I just think it certainly helps me kind of get the logic and get this next step correct. So I'm trying to prove this. I know this is true. So it's true that this is less than this. I'm trying to show that this is less than this. So if this is less than this, it must in turn be less than that. Okay, so this is less than this is less than that. So my next step then will be, so you're kind of nearly bringing it in at the end here. So is greater than 2k plus 6, but this one less than this one. So 4k plus 3 is greater than 2k plus 6. So true if. So k is to one side, so bring that 2k over, 4k minus 2k is 2k. Bring the 3 over, 6 minus 3 is 3. So 2k is greater than 3, divide both sides by 2. K is greater than 3 over 2. Okay, so this is true for k is greater than 3 over 2. I only want this overall thing to be true for numbers bigger than 5. So if this statement is bigger for numbers bigger than 1.5, it's certainly bigger overall for numbers bigger than 5. Okay, so as I said, there is sometimes you'll see a little bit more detail here, but I think you're just fine from here to just skip straight into, therefore, Pn is true for all n's greater than or equal to 5. N is a natural number. Okay, that's it. Solution done. Just to kind of talk through it maybe a little bit. So just this k is greater than 3 over 2. That doesn't mean you've proved this for k is greater than 3 over 2. So like 3 over 2 is 1.5. So a number bigger than that is, say, 2. What if I sub 2 in here? 2 squared is 4. 4 times 2 is 8, plus 3 is 11. So is 4 greater than 11? No, it's not. So you haven't proved the entire thing is greater than, it works for numbers greater than 3 over 2 here. You've just proved kind of this bit here. All right. So it's still the kind of original one you're going back to. So you want, I suppose, k greater than a number smaller than this here. But what would mess us up is if this only worked, say, for k's bigger than 6, but we're trying to prove the overall thing greater than or equal to 5. So that's where maybe you'll have gone wrong. If something like that happened, I would say the most likely thing is maybe you've just got these the wrong way around. So just check that. It's easy enough to kind of mix up the logic of that and maybe put the wrong thing on the wrong side of the inequality. Just to kind of try maybe talk about the kind of logic of what I'm doing here a little bit. To kind of adapted a little bit from the start of the inequality bit in your book. So let's say you've got a number line and you've got x and you've got y and you've got z. And what I'm trying to prove, say, is that x is bigger than z. Okay, this one's bigger than this one. So to prove that x is greater than z, and let's say I have assumed that x is bigger than y. Okay. So trying to prove x is bigger than z, have assumed x is bigger than y. So this overall thing is true if y is bigger than z. Okay, so trying to prove this, have assumed this. So if this is bigger than this, you've bridged that slight gap. Okay, so true if y is bigger than z. Now, I suppose what's complicated about these ones is we're dealing in expressions with variables in them. Okay, so these things will all change value depending on what your n is or what your k is, depending on what value you're using. So like this would be really easy and straightforward if it was just 2 and 4 and 10, if they were just fixed points on the number line. The issue is they are moving around depending on what your numbers are. So it's possible for the kind of y bigger than z to kick in a little bit earlier than the x is bigger than z. So I'm trying to prove x is bigger than z. It's true if y is bigger than z. It's quite possible that it will look like this, and this bit will kick in for variables, say, bigger than 3/2, but that this doesn't kick in till variables bigger than 5. But if you can show this, you are kind of bridging this gap we need to prove this overall thing. Okay, it is a little bit tricky to get your head around, I would say that, but hopefully that kind of helps you. Look, the first few examples I'm going to give you in the book are very like this example and this example here, and you will see there is quite a lot of similarities between them. I could have kind of done this logical explanation on this one as well. It will be pretty much the same for that.